Alright, here we are in section 12.1, and we're ready to get started. We're rocking a little Mozart today from the 1780s, and it's very important why we chose something from the 1780s, because I got a little story to tell. On the left here, we have a guy, Carl Friedrich Gauss. He was called the Prince of Mathematics. He is one of the most famous mathematicians of all time. On the right, mean teacher. Here's the scenario. Carl Voss is in class, rocking out to some Mozart, probably too loud. Mean teacher. That is way too loud over there, Carl. You got to turn that down. I'm rocking, man. I'm rocking. Here's what I'm going to give you for a punishment. You need to add up all the numbers from 1 to 100. Okay. So Carl proceeds to look at the problem for just a few moments. And while the rest of us would be doing 1 plus 2 plus 3, Carl sees right away that 1 plus 100 equals 101. And 2 plus 99 equals 101. And so on and so forth. And there's going to be 50 of those. So he writes on his paper, 50, 50. Circles it and is done. Now he didn't do any of this work, and he had no work written down, but he showed the teacher that he was done within 3 or 4 seconds. Carl, you go to detention. This is disrespectful. I asked you to add those numbers up. Although his answer was correct. Carl was the first person to ever determine these types of things, and that's what we're going to be learning about here in chapter 12. Now, the one thing that I left out of the story is that when this happened, Carl did not look like he does here, like a 45, 50-year-old man. Carl was in 3rd grade when this all occurred. So, if you can imagine, the Prince of Mathematics in 3rd grade was pretty doggone smart. So let's see where this all goes from here. All right, let's take a look here. Let's get rid of some of this stuff. Let's do this, and there it is. So a sequence. A sequence is a function of whose domain is the set of consecutive integers. So generally, when we talk about a sequence of numbers, there's 2 parts. There's the domain and there's the range. The domain is always going to be 1, 2, 3, 4, just consecutive integers. Sometimes it doesn't have to start at 1, but generally it's assumed if they don't show it that it's going to start at 1. Let's get Mr. Voss and mean teacher out of here. So the domain is 1, 2, 3. The terms are the values in the range, and we'll talk about that in just a moment. The values in the range. And the series would be the sum of all of the terms, and summation notation is the notation for a series that represents the sum. And so this is just a way we're going to write the sum, and sigma notation is another way we're going to write the sum. So we'll work with that in just a moment. I have no idea why this stuff's not going away, but we'll just do this to it to get it out of our way. There we go. Okay, so a sequence. A sequence is a function whose domain is the set of consecutive integers. If a domain is not specified, then it starts with the number 1. 1, 2, 3, 4. If they say the domain starts at 5, it would be 5, 6, 7, 8. There, that's how that works. And the range is called the terms, and that's what we just said in our definitions. A finite sequence has an end, like 2, 4, 6, 8. And an infinite one, as you might be able to guess, does not end. 2, 4, 6, 8, dot, dot, dot. On and on and on, forever and ever. A sequence can be specified by an equation or a rule. We'll show you some specific ones in a moment. For example, both sequences above can be described by the rule a sub n equals 2 times n, or f of n equals 2 times n. Okay. All right, page 2 here. In example 1, it says write the first 6 terms of this sequence. And what we have is a sub 1, and what I like to think about is I kind of draw a table as a sub n is the term value, n is the term number, and I think about that being the domain 1, 2, 3, 4, and then the term value is when I put the 1 in there. So if I take this thing right here and I put a 1 in there, I get 2 to the 1 plus 1. 1 plus 1 is 2. 2 squared is 4. And 4 goes right there. Let me make that a little bigger so it's easier for me to write out. So if I have 2 to the 1 plus 1, and then I have 2 to the 2 plus 1, and 2 to the 3 plus 1, and 2 to the 4 plus 1, 2 to the 5 plus 1, 2 to the 6 plus 1, I end up with 2 to the 3rd, which is 8, 2 to the 4th, which is 16, 2 to the 5th is 32, and 64, and 128. So therefore, my sequence of numbers is 4, 8, 16, 32, 64, 128. That's the terms of the numbers. Okay? Let's see what we have here in example 2. In example 2, it says describe the pattern. Write the next term and write a rule for the nth term. So let's see what's happening here. Can you see what's going on with these numbers? 1, 4, 9, 16. That's the first one. So you have to start to look at those numbers, and this is the hard part of the whole lesson. What's happening? 1, 4, 9, 16. Well, I know 16 is a perfect square, 9 is a perfect square, and 4 is a perfect... Oh, it's 1 squared, 2 squared, 3 squared, 4 squared. Dot, dot, dot. So would we call that finite or infinite? Hopefully you see that that's infinite because the dot, dot, dot makes it infinite. So maybe I want to write that down somewhere. Infinite series. All right. The next term is a sub 5. You see this one is a sub 1, a sub 2, a sub 3, a sub 4. A sub 5 would be 5 squared, or 25. A rule for this would be a sub n equals n squared. Okay? Let's take a look at the next one. Next one's a little harder. 0, 7, 26, 63. Pretty tough stuff. I don't imagine most people are looking at that and saying, oh, well, that looks like n, or 1 cubed minus 1, and 2 cubed minus 1, and 3 cubed minus 1, and 4 cubed minus 1. And the next term would be 5 cubed minus 1. I wouldn't imagine. 5 cubed minus 1 ends up being 125 minus 1 is 124. So the rule for that would be n cubed minus 1. You go ahead and try that checkpoint here and see how you do. You guys are going to do 1 and 2. Just take a moment. Pause it. Come back. All right. Welcome back. Let's see how you did. Hopefully, maybe you did like I like to do. A and a sub n like this. I like to do it that way. 1, 2, 3, 4, 5, 6. And if I put a 1 in there, 3 times 1 is 3, I get negative 4. Put a 2 in there, I get negative 1. I put a 3 in there, I get 2. I put a 4 in there, I get 5. Hopefully you're seeing that this is going up by 3 every time, because it is following a pattern, because it's a slope 3. If you think about things in lines, it's a slope of 3, rise over run, right? So up 3 and over 1, and 11. So hopefully you saw that. And on the next one, for this sequence, negative 3, 9, negative 20. Oh, these are all 3 to some power. Well, negative 3 to the first power would be negative 3. Negative 3 to the second power would be a positive 9. So it looks like we have a sub n equals negative 3 to the nth power. Let's see if it works for number 4. A sub 4, negative 3 to the 4th power. Yep, that equals 81. So it worked. All right. Series and summation notation. Now these are the ones that we add up. And so sometimes you can do it, sometimes you can't. You got to pay attention to what we have going on there. You can use summation notation. So what I'm going to put right here is the word summation to write a series. And it looks like this. It has this cutesy little formula to it. The I is really kind of like the N that we were talking about earlier. And what we do with that is when I see that 2I, and I starts at 1 and ends at 4. That's what that means. So I have 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4. Okay, that's how I'll do that. So for both series, the index of summation is the same thing, right? And it's the letter I. And the lower limit of summation is 1. The upper limit of summation is 4 for the finite series, and it's the sideways 8. Nobody knocked the 8 over. Nobody punched 8 in the head, right? That is called infinity. All right? The summation notation is also called sigma notation. That's just another way you might see that. Sigma, S-I-G-M-A. That thing is called the Greek letter sigma. So if you go to a college campus and you see that on the buildings, it means sigma. All right? Let's take a look at example 3. In example 3, I have 4 plus 7 plus 10 all the way to 46. And this is finite. It's stopped. This one's infinite. That one keeps going on forever. Notice that the terms 3 times 1 plus 1, the first term would be that. The second term would be 3 times 2 plus 1, 3 times 3 plus 1, and the last term is 3 times what plus 1? What do you think? 3 times what plus 1 is 46. Hopefully you said 15. I don't know if I can get 15 to fit in there. 15. So a sub I, my terminology for a sub I is going to be 3 times I plus 1. Let me try to make this whole thing a little bigger. It's easier to write. All right, 3 times I plus 1. So 3 times I. Hold on, let me get my eraser. Alright, so right here it should have said 3 times I plus 1. Okay? Where I is going to go from 1 all the way to 15. The lower limit of the summation would be 1. The upper limit would be 15. Therefore, the whole thing is going to look like this. Sigma, stop at 15, I equals 1 on the bottom. So that says start at 1, stop at 15, and do 3I plus 1. And that's how we'd write that. If you look at the other one, if you look at the denominators, see this is 1 over 1. We're looking at this series up here. 1 over 1 and 1 over 8 and 1 over 27 and 1 over 64. I hope you're looking at those, and maybe you are, maybe you're not. I hope you're seeing that that's 1 over I cubed. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. The lower limit of this summation would be 1, but the upper limit is infinity. So when I write it, I have I equals 1 on the bottom. On the top, I have infinity. And then I just write 1 over I cubed. Okay? All right. You guys do this checkpoint. Take a moment and work on that and see how that goes. All right, welcome back. Now, we're just writing summation notation, so hopefully you all at least got to this part of it. Hopefully you said I equals 1. That's the easy part of it, right? And when I look at those things, it looks like this is 7 times 1, 7 times 2, 7 times 3. This, 7 times 11. So, hopefully you got 7i there. Let's take a look at these. Now these ones are negative. Negative 4, negative 8, negative 12. 1 times 4, 2 times 4, 3 times 4. Well, very similar. I is going to start at 1, which is customary. Not always, but customary. Usually what happens. It's going to go to infinity because the dot, dot, dot. And I have negative 4i right there. So hopefully you got that. Let's take a look at example 4. Now in example 4, they're going to actually find the sum of this series. And it starts at 3 and it goes to 5. So I have to do 2 minus 3k. K is instead of I here. So we're going to do 3, 4, and 5. 2 minus 9 is negative 7, plus 2 minus 12 is negative 10, plus 2 minus 15 is negative 13. And I end up with negative 30 on that one. So you're just going to be asked to find those. Now they have some special formulas also, and here they are. Here's 3 of them that will help you. So let's use this one to find the summation from 1 to 32. Who did this one? Who was the guy? Anybody extra credit for this one? Name starts with a G. A-U-S-S. Rocking to this music. Way too loud. A little Beethoven from the 1780s. Getting in trouble. Add up all the numbers from 1 to 100. Or 1 to 32 in our situation. And how would I add up all the numbers from 1 to 32? Well, you simply go through the steps. And we have a formula right there. It's sum of all... Actually, it wasn't this one right here that he had to do. Sum of the first n positive integers. It was the middle one that he was asked to do, where it was I. Okay? So he's going from 1 to 32, so he's going to have 32 times 32 plus 1 divided by 2. Well, that's 32 times 33 divided by 2 is going to equal 528. Now remember what Mr. Gauss did. Mr. Gauss did 100. So he did 100 times 101 divided by 2. Now he didn't do it this way. He discovered this later. But what's 100 divided by 2? 50 times 101. That's what he did. So that's what he did in 3rd grade, right? You guys go ahead and do checkpoints number 5 and 6 and see how you do. Alright, I hope you got something like 160 for the first one and 7714 for the last one. Alright, good luck.